Hello, my name is Najib Khan, and I'm the project lead and back-end developer.
My name is McKinley Harold, and I'm the front-end developer.
My name is Nicholas Cruz, and I'm the creative design lead.
My name is Thomas Claggett, and I'm the researcher and analyst.
And this is
Zeus Auditing.
Buildings account for a majority of energy consumption globally. For carbon dioxide emissions, that's 40%. Energy consumption and carbon dioxide are the two most paramount barriers to future sustainability. But 50% of all industrial energy is wasted. And the most harmed by this waste? Low and middle income households and small businesses. Around 27% of all US households struggle to pay energy bills, and as a result, homeowners keep their homes at unsafe temperatures. Not only does inefficiency raise the bills, it kills your health too, as it causes respiratory problems. It's for these reasons that the United Nations outlined Sustainable Development Goal number 7, energy. The focus of our project is Target 7.3, where we look to improve energy efficiency by tackling the most disparate setting in buildings.
The most common way to tackle energy efficiency in buildings is to conduct an energy audit. An energy audit is a detailed report of how the client can improve energy use, providing options, energy models, and estimates on savings. However, energy audits require skilled auditors and as a result are costly and time-consuming. The barrier of entry makes it so that energy auditing is a privilege for large enterprises. Residential homeowners and small businesses are unable to contend with the demands of the audit. Project Zeus aims to bridge this gap, allowing homeowners and small businesses to utilize previously unavailable energy auditing to improve efficiency. Armed with this auditing, they can reduce the energy bills and improve the comfort of their building.
Project Zeus is a web application powered by an Arduino that uses advanced thermal imaging technology and image analysis to project cost savings. Our intuitive interface democratizes energy auditing, allowing small business owners and low to middle income household owners to retrofit their buildings and project their savings using our calculator.
Our first design idea was to create a storefront for energy-efficient appliances that could calculate estimated savings in energy over time. While we helped consumers to save money, we were saving the environment by using less energy.
The problem with our storefront was that it didn't address the root of the inequity. Creating a marketplace would be helpful, but it's more helpful for well-off consumers. It's for this reason that we started to research ways we could help disadvantaged users in the field of energy auditing.
So we shifted gears. Project Zeus took form as energy auditing software. In early stages of development, Zeus started as a desktop application, much like Microsoft Word or Google Chrome. We designed the application in Qt Designer. Here's the problem though. How could we justify a non-technical user downloading experimental software and dependent packages to run an application which gave no promise on improving savings? Not only that, but it was difficult to import and display the heat map in the application.
To make the project more accessible, after consulting with local business owners, we moved to a web-based framework. There weren't many concessions other than the aesthetic of a desktop application. Now, accessing Zeus is as simple as typing a URL in your web browser.
Because we found insulation and heating to be the greatest source of energy inefficiency, we looked for mathematical models. You can determine heat flux or the difference in temperature across the material using Fourier's law of heat conduction. U values and R values determine how well materials conduct heat, and because they're commonly available from building codes, we're able to integrate these numbers into our calculation. To get the temperature gradients from sensors, we landed on two options, using a heat flux sensor or using a thermal camera. A heat flux sensor is more accurate and generalizable, but at nearly 8 times the cost. A thermal camera would only cost $50, including wiring.
Let's start with our thermal camera. Our Adafruit AMG is wired via I2C to an Arduino. It's the most economical camera while also being very simple to assemble, making it easy for non-technical users to connect. When you point the AMG towards the surface, it senses the infrared radiation and returns an array of numbers that correspond to the temperature values of each pixel on the camera. The Arduino is programmed to capture frames of the thermal camera based on user input. When the start button is pressed by the user, the computer sends a byte encoded S to the Arduino, giving the signal to start picking up the thermal frames. When the stop button is pressed, a byte encoded X is sent to the Arduino, giving it the signal to stop sending frames. When the snapshot is pressed, a byte encoded R is sent, telling the Arduino to save the current frame to the directory.
Moving on to the backend, we need to import a few important libraries before we begin display and analysis. To fetch and show the thermal image, we use Flask to create API endpoints to use the thermal image from the Arduino serial connection to the website. We create a separate thread to split the computational work across the CPU. Next, we move to the analysis module, where we import OpenCV, NumPy, and Matplotlib. We create data classes to compartmentalize the analysis into thermal analysis, financial analysis, and visualization. Then, we define functions that perform a Gaussian blur to reduce image noise and interpolate the raw image that is given by the thermal camera into a higher resolution. This processed image is then analyzed by using OpenCV's gradient operators. These are differential operators, meaning that how they see the pixels and the temperature change is how they find the edges that there may be a heat loss at. Sobel is a first derivative operator, while Laplacian is a second derivative operator. These edges are then analyzed to determine if they're problematic, assigning a score to these edges. A quick analysis outlines points of heat loss via the scoring algorithm, while a detailed analysis pushes the financial analysis using Fourier's law to determine how much heat is lost based on the parameters that the user gives. Recommendations are then given to the user given priorities based on the severity of the edge. Meanwhile, in another thread, we're creating a heat map using matplotlib. These two threads functions are then called back together within the get thermal data and get heat map function, creating an API endpoint that provides the information for the user on the website. Right here, we got the website up and running. Our first tab that we have is an information tab where we tell you guys exactly what we do for our project. Next, we have the parameters tab, and these are the different parameters that the user is going to input manually, and right here are automatically picked up from the camera. Next, if we go into the camera tab, this is the heart and soul of our project. Right here, we have a start button, and that'll get to start setting frames. As I move this camera around, you can get it to see that it's moving around, and also the pixels are changing. Next, I can press a stop button on here, and that will cause the frame to freeze. After that, I can take a snapshot and it'll automatically send it to my directory. If we run a quick analysis, it's going to glow a bit in the points where there's heat loss at the lowest pixels. Next, if I click a detailed analysis, it's going to give me feedback on exactly how much heat flux is going through the wall. As you can see the values here, our insulation is pretty solid as our heat flux is pretty low and our energy savings are pretty good.
Our backend is coded completely in Python to simplify data analysis. Our front end is coded in JavaScript, HTML, and CSS. As a combination, this allows the web application to be interactive and also simple to both navigate and build.
Our prototype is functional and effective, but the low resolution and slow response time of the thermal camera leaves a bit to be desired. However, we have to consider costs in order to make our prototype accessible. In the future, the thermal camera could be moved into a phone camera using a much higher resolution and cutting out the Arduino communication. This would make our analysis algorithm more precise and accurate, as the edges will be confined to a much smaller space.
Another ambitious addition would be to train a machine learning algorithm. This algorithm would detect the surface area of the wall, the material of the wall, and would use the values in the financial calculations. This would cut the need for the user to input these values manually. Machine learning, however, is very expensive and time-consuming to train. Given more time and financial investment, this could be feasible.